let us look at the rules for eliminating for all and exist. So how do you eliminate for all? Basically, you remove the quantifier and the variable is get replaced by another term t. Notice that there is no side condition here. You can replace with any term. One implicit side condition is here. The substitution must be defined. Otherwise, this writing of ft makes no sense. Now we have three rules so far. So now we can do actual proofs. Okay, so let's see. If you have for all x fx, then you can derive that then there exists an x fx. Well, let's see how it gets done. So you have a sigma proofs for all x fx. Then you say, okay, I can derive f of x because I simply take x out and put back x in, because there is actually a substitution happening. You're not simply removing for all x, you are taking x out and putting the back x in. By the process is such that it just gives you defined substitution. Okay, now what we can do is that we can use exist intro rule to apply here, and then you get this formula out. The major point is that you need to check the side conditions required when you apply exist intro, and please check those, that why they work here. Yeah. One important point to note here is that the proof doesn't work in the reverse direction. Okay, you try to go bottom to up, you will see that you need to eliminate exist. We don't have a rule which allows me to just put an x here. Okay, so far we have not seen. Okay, so let's look at one more proof which will give it more action. Okay? So let's suppose I want to prove this. Okay, so I will take this formula and another formula like this, which is basically negation of this guy, and prove that this thing holds true, and then Boolean reasoning will give me this thing. So let's see how we go about doing it. Okay, so we got here, right? So first thing is I have for all by assumption, then we apply for all lm, and we obtain py or qy. Yeah, so right, so we can do by assumption. You can also introduce this guy, not x px, and now what we do, we assume py, and then you derive py, and since I can do intro here, I can exist intro, and then which is contradicting with this and this guy. This tells me that I can derive not of py, and using not of py I can apply with this guy and derive qy. Yeah, so I got qy, and using qy I can simply see that there is no mention of y anywhere in this side, so therefore I can do for all x qx. Then I am done here because the rest of the reasoning is propositional. Let's look at this pesky issue of substitutions being defined. Okay, so when it gets not defined, and how do you take care about how you put your mind around it? Okay, in any proof rule, what happens is you need to choose something called fz. There will be a leaving term t, which will be getting out of your antecedent, which will maybe probably written as ft, and arriving term which will be coming in, so will be the consequence will have fs appearing. Okay, so there are two substitution happens when each time you apply a proof rule. Okay, so that both of them should be defined proof rules. What restrictions do I get here because of this definedness has to happen? Okay, so antecedent and consequence have this ft and fs, right? It's clear. So let's suppose an example. Okay, so we have this formula fz, and the z is occurring at several places. Okay, here, or maybe here, or it's not occurring here. And so these are the four distinct scenarios. One, when z appears as a free variable. The one scenario is z gets quantified in a scope. Okay, and another scenario is in a quantified scope, z is not even there. Okay, and in another scenario, z occurs in a quantified scope. Okay, so what kind of restriction, what kind of substitutions am I allowed, what is not allowed? Okay, so you should not worry about the free z occurrences. You can substitute with anything, it should not be a problem. Okay, if you z get quantified, substituting z to something else doesn't matter here, because z, the substitution, as soon as you try to go inside, gets disabled, nothing gets changed. So this is also a safe situation. The other situation is that doesn't occur in that context. Okay, so you go inside, it's no restriction because you're not substituting anything here, so it's safe. Okay, the troubling case is this last one, when z occurs in some context and there is a quantified variable sitting on top. So now when your z is going out, another term is coming in, let's say t or s, they cannot have y. If they have y, then there is a problem. You are doing wrong kind of substitution. Okay, so this you need only, this is a real restriction you have. Okay? And be mindful of that. Okay? Now let's get back to our quest of defining all rules for the exist and for all. So we have seen for all we have intro and lm. For exist we have seen an intro, but what is lm? Okay, so lm should be natural, right? So for example, if we say that if there is something, we should be able to choose that thing. If say there exists x fx, then I should be able to say f of c or whatever. Okay, but it should not be an arbitrary choice. It cannot behave like as a for all. Like for all, when we did the elimination, we just simply put a term in. Yeah? So that should not be the behavior of exist. So how do we handle it? Okay, one example will clarify this. Let's suppose I want to prove this theorem. If there is a door in the building, I can steal diamonds. Some statement, nothing in particular about it. Just try to understand how exist plays out. Okay, so we have something like there is a door. How do you write this theorem? Okay, so if you want to prove this theorem, what will happen is you'll say, okay, there is a door x. Okay, you assume this door x is there. Then you work out the details of your robbery. Okay, and then finally you say I stole diamonds. Okay, you prove this statement by applying some bunch of rules, and then you say therefore the theorem holds. Informally, how would you write it? Okay, you assume that there dx, then you prove this dx, x is a door. You write down the details of robbery in a formal setting. Then you say some predicate, you will prove that diamonds are stolen. I'm using as a symbol stolen. And now what you do, you apply the intro rule. Now you get dx proves stolen, and then this tells me this theorem. Then if there exists an x dx, then implies stolen. Okay? From here to here, I should be able to make the jump. Paradoxically, lm for exist introduces exist symbol, however on the left hand side of an implication. Okay. One important point to be noted here is that this stolen does not have variable x appearing. So this is a typical situation when you assume something and you prove something, that x doesn't show up in the stolen. Okay, if you have this kind of proof, okay, fy implies g, what you can do, you can introduce this, there exists x, fx implies g, and you need to show that y does not appear in sigma anywhere or in g. Okay, y is not allowed to appear here or in here. Okay, it's very much like for all restriction. Okay, so let's suppose I want to prove this. Okay, how do I prove it? Okay, so first I will assume ax bx. Okay, and from there assumption I can prove this ax and bx. Then from there I get ax out. We have seen this before. Then I can use intro for the exist and I get exist x ax. Okay, so far you can check all the side conditions, they have been satisfied or not. Okay, now what we can do, we can apply the intro. I got this form. This form matches with the form that we need for exist lm. So therefore I can apply the exist x ax and bx implies exist x ax. This proof structure will repeat it again and again. Okay, so you want to assume this guy and prove this, right? So you start with this only and then you prove, okay, from here to here, and then you are allowed to derive this.